everyone, welcome to my class. Today we are going to learn a triple integral in spherical coordinates. Let me start the class with a recall. So far we studied triple integrals in Cartesian coordinates and in cylindrical coordinates. In Cartesian coordinates, the triple integrals template is we denoted by I equals to triple integrals of function of x, y, z over a three-dimensional bounded region E, and we integrate with respect to volume element dV. Similarly, in cylindrical coordinates, our triple integral template is triple integrals of f of r cosine theta, r sin theta, z, and our volume element is r dz dr d theta, and the integral is in this order: dz dr d theta. Inner integral is z integrals, middle integral is r integrals, and outer integral is theta integrals with appropriate limits. Now in today's class we are going to learn our spherical coordinates and triple integral in spherical coordinates. First, let me give you an introduction of spherical coordinate systems, and then later on this Cartesian coordinates template of triple integrals, we want to find the representation of x in spherical coordinates. We're going to find out the representation of y in spherical coordinates. Similarly, we're going to find out a representation of z in spherical coordinates and replace those x, y, z by those representations, and also the volume element in spherical coordinates. Great. So first let me give you the definition of spherical coordinates. Spherical coordinates are represented by the order triple rho, theta, phi. By the way, the spherical coordinates are a little bit challenging than comparing to cylindrical coordinates, and most of the times people find kind of misleading for this phi limits. So please try to understand. So let me describe this point on this middle diagram. So the point P is in the space rho, theta, phi. This rho is a distance from origin to the point P, and theta is a angle made by the projection of rho on xy plane, so r, and this projections made to the positive x-axis. So in another word, the theta is the same as in the polar coordinates, and phi is the angle made by this line segment OP, or the radius, with the positive z-axis. So this angle is phi. Okay, great. So in another word, we can say the spherical coordinates is a generalization of polar coordinates from 2 dimensions to the 3 dimensions. Great. So then this point rho, theta, phi, now I am on my first diagram, which is a point on the outer surface of the sphere. Then that point generates a sphere. Great. Next, let's concentrate on this middle diagram, on this shaded triangle. So this angle is phi, angle of reference, and this angle is 90 degree. So this is rho is hypotenuse, this is z, which is base, and this is perpendicular, which is this value rho sin phi. So using this Pythagorean identity here, that relations, then this gives us the z is rho cosine phi. So z is rho cosine phi down here. This is, now we have a conversion of z from Cartesians to the spherical is z equals to rho cosine phi, and this one is rho sin phi, and which is same as this r. This r is now rho sin phi. So now we use this r, the r used in cylindrical coordinates, now we can replace by rho sin phi. And then we mentioned rho is a distance of outer surface of the sphere in the first diagram. If you wanna look here, rho is the radius of the sphere. So then rho square equals to g square plus r square. So rho square equals to, this is x square, this is y square, and this is z square. So rho square equals to x square plus y square plus z square. Now let's talk about the limits. For the rho is obviously positive, and which is the radius of the sphere. And theta is the same angle as polar angle, so theta goes 0 to 2 pi, and then the phi only runs from this g all the way to down here. That means positive z to negative z. That means, in another sense, phi runs from North Pole to the South Pole. And when phi is pi over 2, which is equator. Great. Now in the aside, I put all the points in one diagram. So p x y z in the Cartesian coordinate, r theta is cylindrical coordinates, rho theta phi is in the spherical coordinates. And one quick remark: for sphere, rho is constant, and for cone, phi is constant, and for the vertical half plane, theta is constant. Now let me go to the convergence formula. So the conversion of Cartesian coordinate to spherical coordinates and also to the cylindrical coordinates. This is the revision from previous sections. We cover conversion from Cartesians to cylindrical coordinates. Now today we are focusing on conversion of Cartesian coordinate to the spherical coordinates. Let me scroll down. Yeah. So x equals to, in cylindrical coordinates, r cosine theta. And we found r equals to rho sine phi here. Let's replace this r by rho sine phi. Then in spherical coordinates, our x is rho cosine theta sine phi. Similarly, y equals to r sine theta in cylindrical coordinate. Replace this r by rho sine phi. Then in spherical coordinates, y equals to rho sine theta sine phi. And z, in the Cartesian z, doesn't change in cylindrical z, remains the same, but in spherical coordinates, z equals to rho cosine phi, we found here. So now we have a conversion formula. And similarly, the volume element in spherical coordinates becomes dv equals to rho square sine phi d rho d phi d theta. Let me emphasize this rho square sine phi. Okay, so this is a additional term to this d rho d phi d theta to form a volume element. So this is important. So now at this time, let's ask questions to ourselves again. How to determine the limits of triple integral in spherical coordinates? So far, on this template on our Cartesian coordinates triple integrals, now we have x representations, y representations, z representations in spherical coordinates, and also we have a volume element dv in spherical coordinates. So next questions, we want to find out what's the corresponding limits here of these three integrals. Let me scroll down again. So the setup of a triple integral in spherical coordinates. So for a special case, in a spherical coordinate system, the counterpart of a rectangular box is spherical ways E, which is given as rho between two constant value a and b. Phi is given between two fixed values c and d, and theta is given between two fixed values alpha and beta. Then this triple integral in spherical coordinates becomes I equals to rho cosine theta sine phi. That's our x. And then y is rho sine theta sine phi, rho cosine phi, and then the volume element rho square sine phi d rho d phi d theta. And with this order, d rho d phi d theta, our inner integral is Rho integral, so whose limits are a to b. Middle integral is a phi integrals whose limits are c to d, and our outer integral is theta integral whose limits are alpha to beta. So now we can extend this formula to include the more general spherical region. For example, radially simple regions where our rho depends on theta and phi. Then these triple integrals in spherical coordinates can be rewritten as, or denoted by I equals to, I copied this integrand function as it is, so f of rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi, and then the volume element rho square sine phi d rho d phi d theta. And for more general spherical regions, rho, the limits of rho depends on middle variables and outer variables, so which is between h1 theta phi to h2 theta phi, and middle integrals whose limits are c to d. The outer integrals is theta integral whose limits are alpha to beta. Great. So this integral is the triple integral in spherical coordinates. Now let me make one small comment here. Usually spherical coordinates are used in the triple integrals when surfaces such as cones and spheres form the boundary of the region of integrations. Okay, so now we are ready to start the example. So let's start the example. Example 0. Again, short and sweet, we are finding the volume of a sphere of radius a using spherical coordinates. Example 0. Find the volume of the sphere x square plus y square plus z square equals to a square. Here, radius is a. So the formula, the volume formula in triple integral is v equals to triple integrals of 1 dv. Our integrand function is 1. So dv equals to rho square sine phi d rho d phi d theta. And then the triple integrals in this order, so rho integrals is inner integrals whose limits are rho equals to 0 to a. And the middle integral is phi. And for this sphere, phi goes from north pole to south pole, so 0 to pi. And for the outer integral is a theta integral whose limits are 0 to 2 pi. Then we can integrate again separately here. So from theta integral it gives us 2 pi, and from the rho integrals, which is rho square, becomes rho cubed over 3, and put the rho limits rho equals to 0 to a. And from the phi integral, sine phi, integration of sine phi is negative cosine phi, and phi goes from 0 to pi. Next, let's plug the values. So 2 pi, write down as it is, and put rho equals to upper limit a, so a cubed over 3, and put cosine phi equals to upper limit pi, so cosine pi is minus 1, so minus minus plus, and to put the lower limit is 0, we need to introduce another minus, so that minus and this minus is plus, so cosine 0 is 1. Then simplify, it gives us 4/3 pi a cubed. Great, so we use spherical coordinates to compute the volume of this sphere. Let me scroll down. Here, great. So let's do another example, example 1. Using spherical coordinate, evaluate the triple integrals. I equals to triple integrals over e of integrand function is x times e to the power x square plus y square plus z square times dv, where the region E is a portion of the unit ball that lies in first octant. Unit ball of radius 1, that means rho's limits are 0 and 1. Then in the first octant, our phi for this unit ball goes from 0 to pi over 2. So only north pole to the equator. And for the theta goes to 0 to pi over 2, 0 to 90 degree. Great. Now let's write down the given in triple integrals with those limits. So then given integrals I equals to x is rho cosine theta sine phi. That's the x equals to x representations in spherical coordinate. Then e to the power x square plus y square z square becomes simply rho square times the volume element dv is rho square sine phi d rho d phi d theta. And with this order of integrations, d rho d phi d theta, the inner integral is rho integrals whose limits are 0 to 1. Middle integral is a phi integral whose limits are 0 to pi over 2. And outer integral is a theta integral whose limits are 0 to pi over 2. I hope this setup makes sense to you all. And in the now next step, write down the theta integrals and the cosine theta d theta. So here basically we are integrating, separating the integral. So that's the theta integrals, that's the phi integrals. So how many sine phi we have? 1 sine phi, 2 sine phi, so sine square phi d phi. And then rho integrals, 1 rho, here is a 2 rho, so total 3 rho, rho cubed times e to the rho square d rho. So let's integrate separately. Let me scroll down. Yeah, better. So the cosine theta becomes sine theta. Oops, that's a typo. It's not phi, it should be sine theta. So the entire derivative of cosine theta is sine theta. The limit of theta is 0 to pi over 2. So sine pi over 2 is 1. So this is the result from the first integral. Let's go to the middle integral. Sine square phi using trigonometric identity. This is 1 minus cosine 2 phi over 2 and phi integrals. Then 1/2 pull outside. The integrals of 1 with respect to d phi is phi minus integral of cosine 2 phi is sine 2 phi over 2. Put phi limit 0 to pi over 2. 1/2 as it is, then phi, put phi equals to pi over 2, and sine 2 times pi over 2, 2 cancel, sine pi is 0. So that term disappears. And put lower value of phi for 0, sine 0, 0, 0 times phi 0. So only we have phi over pi fourth. This is the result of middle integrals. Now let's move to the third integrals, rho integrals. So this is a good candidate for u substitutions and integration by parts later. So let's put u equals to rho square. Then its derivative is du equals to 2 rho d rho. Then also rewrite rho cubed equals to rho square times rho. And then this rho square is in the new integral simply u, e to the u, and this rho times d rho is from here, du over 2, which is here. So then pull 1/2 outside and use integration by parts formula, which is given here. For u eu, this gives you this result, 1/2 u times eu minus eu. Then substitute u equals to rho square, 1/2 rho square, e to the rho square minus e to the rho square, and put rho limits 0 to 1. Then put rho equals to 1 and put rho equals to 0 and subtract those two values and simplify, it gives you 1/2. So this is the 1/2 is the result of third integrals. Then our final answer for this triple integral is we need to multiply these three results. So 1 times pi fourth times 1/2 equals to pi 8. So we found the value of these triple integrals using spherical coordinate, which is pi over 8. Great. So let's move on. Let's do example 2. This is better. Excuse me. So example 2, it says find the volume of the solid that lies within a sphere of radius 2 above the xy plane and below the cone. So let's sketch the surface here. Sphere is this outer curve is a sphere above the xy plane, so only the upper hemisphere. So and then the cone is here. Cone is here, and we are finding the volume of the solid which lies within a sphere. So below the sphere, and also below the cone, within a sphere and below the cone. So below the cones, this part, and above the xy plane, so this shaded part. So our solid is this shaded part. So let's compute the limits. Okay, from the sphere, our Rho's limits are 0 to 2. So this is clear. Now let's talk about the phi limits. Phi is the angle made by Rho to the positive z-axis. So we are talking somewhere here. So let me use this cone equation. So cone equation is z equals to radical x square plus y square. Then put the corresponding value of x and y and z in spherical coordinates. So z equals to rho cosine phi, and then put x equals to and y equals to the corresponding values of in spherical coordinates and square them and take the radical. That gives you simply rho sine phi. And then from these relations we got phi equals to pi over 4. Divide the sine phi by cosine phi, which is tan phi. Tan phi equals to 1. You can cancel rho, so phi is pi over 4. So that means this angle is pi over 4, but I am interested on this angle, so which is then phi ranges from pi over 4 to pi over 2. So now we found the phi limits. And now to find the theta limits, we need to simplify these two equations, means find the cross sections and project down on the xy plane. So let's solve these two equations. So put z equals to radical x square plus y square in this sphere equation. Then this becomes x square plus y square plus x square plus y square equals to 4. Then the next step, 2 times you add 2 times x square plus y square equals to 4. Divide by 2. This gives you x square plus y square equals to 2, which is this projection of these cross sections, which is a circle of radius radical 2. And to find the theta is 0 to 2 pi. Great, so now we have all the limits. Then let's write our formula. So using triple integrals to find the volume is simply v equals to triple integrals of 1 dv. Oh, this one is to be 1 here, so that's again another typo. So then dv equals to the volume element in spherical coordinate is rho square sine phi d rho d phi d theta, and inner integral is rho integral, whose limits are 0 to 2, we found here. Middle integral is phi integral, whose limits are pi fourth to pi half, and then outer integral is theta integrals, whose limits are 0 to 2 pi, we found here. Great. Now let's move on. Now we can integrate separately here. So from theta integrals we got 2 pi, and now from phi integrals, the entire derivative sine phi with respect to d phi is negative cosine phi, and put the phi limits are pi fourth to pi half. And from the rho integrals, integration of rho square with respect to d rho is rho cubed over 3, and put rho limits 0 to 2. Great. Then let's put the corresponding values here, upper limit and lower limit. Then simplify. This gives us 8/3 times radical 2 times pi. So that's the volume of the solid which lies within a sphere above the xy plane and below the cone, given in example 2. Awesome. Let's move on. Let's do another example, example 3. Evaluate the triple integrals given in Cartesian coordinate by changing to the spherical coordinates. Okay, so given triple integral is I equals to, outer integral is from 0 to 1, middle integral is from 0 to radical 1 minus x square, and inner integral is from radical x square plus y square to radical 2 minus x square minus y square of the integrand function is xy, and then order of integration is dz, dy, dx. So that means this inner integral limits is the z limits, and then y is in the middle integral, and x integral is the outer integrals. So let's find out the limits for rho theta phi for spherical coordinates. Okay, so from these inner integrals, the z bounds are cone and a sphere. So cone and a sphere, then our phi limits are between 0 and pi/4. And from the sphere of radius radical 2, our rho's bound are 0 to radical 2. So rho lies between 0 and radical 2. So next, now to find the theta limits, let's look at these middle integrals and outer integrals. So this middle integrals is a y bounds here. So y equals to 0 to y equals to radical 1 minus x square. You square that relations both sides, gives you y square equals to 1 minus x square. Then rearrange the term, this gives you x square plus y square equals to 1. Wow, that's a circle of radius 1. And go to the outer integrals, we have the x bounds from the outer integrals, that is x integrals, whose bounds are x equals to 0 to 1. So then this 2 domain just gives me a quarter circle in first quadrant. Then my theta ranges from 0 to pi/2. Hopefully this computation of or determination of these limits makes sense to you all. Then let's start from the question. So the given triple integrals I equals to, let me start for the integrand function. So x is rho cosine theta sine phi in spherical coordinate. Y is rho sine theta sine phi in spherical coordinate. And our volume element in spherical coordinate is rho square sine phi d rho d phi d theta. And now in this order, our inner integral is rho integrals. So the rho limits are, or rho bounds are 0 to radical 2. And middle integral is phi integrals, whose bounds are 0 to pi/4. And outer integrals, theta integrals, whose bounds are 0 to pi/2. I hope this setup makes sense to you. Now we converted the given triple integral in Cartesian coordinate to triple integral in spherical coordinates. Now let's evaluate. Again, we can separate the integrals here. So one is theta integrals, one is phi integrals, and one is rho integrals. Okay, let me put this both pages together here. So from the theta integrals, cosine theta sine theta, so we know the trig identity. Sine 2 theta is 2 sine theta cosine theta. So cosine theta times sine theta becomes sine 2 theta over 2. Then the theta integrals. Now I'm talking the first integral. So the entire derivative of sine 2 theta is negative cosine 2 theta over 2. And multiply this 2, 4. So negative cosine 2 theta over 4. Put the theta limit 0 to pi/2. And put upper limit. So cosine 2 times pi/2, 2 cancel, cosine pi is negative 1. So we have negative, and this negative positive. And to put the lower limit, put negative, so that makes it positive, and cosine 0 is 1, so 1 plus 1 is 2, 2/4 is 1/2. Just a simple algebra here. Great, so we found the first integral. Let's go to the middle integrals. So the middle integral is phi integral, which is sine q phi d phi. First rewrite this sine q phi as sine square phi and sine phi, and convert sine square phi equals to 1 minus cosine square phi. I use trigonometric formula here. And then then I have two integrals here. I can multiply the sine phi inside, so sine phi times 1 is sine phi. I can easily compute the integral of sine phi. And then another integral is negative cosine square phi times sine phi. So then this is a good candidate for u sub. So let's put u sub equals to cosine phi, and its derivative is du equals to negative sine phi d phi. And we can also change the limits for new integrals. So when phi is 0, cosine 0 is 1, u is 1. When phi is pi fourth, cosine pi fourth is 1 over radical 2. So now we have u limits. Then then let's rewrite our phi integral here. So sine phi times 1 is sine phi times minus cosine square phi is sine phi times cosine square phi. Then use u substitution, which gives you the u equals to cosine phi, so cosine square is u square, and sine phi d phi with the minus, so minus sine phi d phi is du, is this integral. Then integration of sine phi is negative cosine phi, and integration of u square with respect to du is u cubed over 3. And also change this cosine phi to u and put u limits. Then this cosine phi is u, so minus cosine phi is minus u, and plus u cubed over 3, and put u limits, which is 1 to 1 over radical 2. If you find this confusing in the u, you can use the phi limits, but you have to resubstitute u equals to cosine phi here. Great. This is the written computation here. So now what do we have? We have negative u plus u cubed over 3, and then the u limits 1 to 1 over radical 2. Then put this upper limit of u and lower limit of u, and then subtract those two values. Then this gives us 2 minus radical 2 over 3. Great. Now let's move on the third integral, which is the Rho integrals. So the integrals of rho to the power 4 with respect to d rho becomes rho to the power 5 over 5, and put limit rho equals to 0 to radical 2, and then now put rho equals to radical 2 upper limit, that means 4 times radical 2 over 5, and you put lower limit, which is 0. So now we have 3 results here. So this is from theta integrals, this from phi integrals, and this from rho integrals. So our final answer is multiply all those 3 results, then this gives us 4 times radical 2 over 30, 5 times 3 times 2, 30, and then times 2 minus radical 2. So we found the value of this given triple integrals in Cartesian coordinates converting to spherical coordinates. Great. So we finished these sections, the triple integral in spherical coordinates today. Thank you.